Our camera had to develop many different technologies. Think about it, in your little digital camera, it has a lens, the size, smaller than your fingernail. And to have a shutter that opens and closes is not so hard. Just a little flap of metal that can go like this, right? On a camera that's this big, it's half a meter in diameter, how do you have a shutter? How do you get a piece of metal going across it so fast? You can't have something lift up and go down. It'll shake the camera, it'll shake the telescope. You don't want shaking in when you're taking astronomical images. Also, if you have something that just sort of moves across like this, then that means that different points on the image will have a different exposure time. Some points will be exposed longer than others, and that's not good, right? So we designed our own shutter that looks like this, and it has some sound effects. Just if everybody's quiet, you might be able to hear it. So what we do is we use two leaves that, because they're on both sides, we can move them either together across the field of view, or we can move one across, wait a minute, and then move the other one across. But because they move across the same direction, we can make sure that the exposure time is constant across the field of view. Every single pixel in the camera has the same amount of exposure to the sky. And when we're not using it for taking astronomical images, we use it for slicing pineapples in Hawaii. This is a picture, one of the very first pictures we ever took with a camera. It's incredible if you're an astronomer. Being able to take a 1 millisecond exposure, 1/1000th of a second exposure with a professional telescope is unheard of. This is a blow up of that picture. It's not that great, but for the very first picture we ever took, it's pretty incredible. A more recent picture that we took was the Whirlpool Galaxy. And to make this image, we take multiple images in different filters. And to make this kind of an image, we really do the same kind of thing that your digital camera does to create a pretty color picture. We take multiple pictures in different filters and combine them together. So, I don't want to talk about any of that. I want to talk about the last thing, which is so I talked about the Pan-STARRS project. And the project I really want to build, though, is this project that maybe is really something the Ecuadorian government could invest in. Because each one of these telescopes systems only costs about $1 million. And our idea is to build multiple versions of this telescope right here. So what I mean by this telescope, by 4 telescopes on one mount. Each one of these costs about $1 million. And we want to build multiple sets of them around the world. We want to start by building 2 and locate them probably in Hawaii or Arizona. And by having 2 looking at the sky at the same time, we will be able to image the entire sky every night, twice. Okay? And by doing so, we can see all the asteroids that are coming in towards us at any time. Now, I have a lot of technical details. I'm not the principal investigator on the project. It's one of my colleagues at the Institute for Astronomy. So we'll have 2 of those telescopes, 2 of those mounts with 4 telescopes each, so 8 telescopes and cameras. These are a lot of details that are not important for people who aren't astronomers. But this here is maybe the most interesting part of it. This gives us, if we build this system, this shows us the amount of warning time that we will have for an asteroid impact. Because right now, the most likely warning time for an asteroid impact is 0. Okay? Right now, we don't know where most of the asteroids are. So if there's 100 years ago, when that asteroid struck Siberia and wiped out 1,000 square kilometers, it came out of nowhere, nobody knew it was coming, and it wiped out 1,000 square kilometers. That is still the same situation we are in right now. That kind of thing could happen tomorrow, and we would not know about it now. Okay? So we want to design a system that can find asteroids like the one that hit in Siberia 100 years ago, and like the one that hit Arizona to create that 1 kilometer diameter crater 50,000 years ago. So this shows the amount of warning time that the ATLAS system can give for asteroids that are 50 meters in diameter and 140 meters in diameter. So for 140 meter diameter, we would have on average about 1 month of notice. Now, a 140 meter diameter asteroid could wipe out a good portion of Ecuador. Okay? That's how big it is. And so, 1 month time doesn't necessarily sound like a lot of time, but would be enough time to evacuate. It would be enough time to back up hard drives, right? Make sure that your Facebook account is all set up before you go somewhere, right? For a 50-meter diameter object, so this is more like the size of the object that struck in Arizona or in Siberia, we would have about a week's notice. Okay, and so this would maybe wipe out 1,000 square kilometers, and 1,000 square kilometers sounds like a big area, but actually it's very reasonable to think that you could evacuate everybody, take a lot of measures to protect the planet from destruction. So Atlas will identify 60% of all the incoming impactors. Why only 60% if we're doing the entire sky every night twice? Is because 40% of the sky is in daylight. And there's nothing we can do about looking for asteroids in daylight. So it's a system that does everything it can, and all that it can, but only at night. This is something I didn't talk about too much, but in 2008, just 4 years ago, there was an asteroid identified before it hit the Earth. It's now called 2008 TC3. It was found about a day and a half, 36 hours before it struck the Earth. It was only about the size of a car, which is one of the reasons why we found it only a day and a half in advance. But we were able, even just with a day and a half's notice, we were able to predict when it was going to hit to within 1 second and where it was going to hit to within 1 kilometer. So it was very, very accurate prediction. And fortunately, it was such a small asteroid that it didn't cause any damage on the Earth. But it did spray a lot of material over the Earth. There were a lot of chunks of rock from this meteor that were found on the planet afterwards. So hopefully, there will be no deep impact in the future. Hopefully, systems like Pan-STARRS and Atlas will identify these asteroids before they hit the Earth. The dinosaurs were as big as this room, but had brains the size of walnuts, right? We're much smaller, but we have very large brains. And the dinosaurs were wiped out by an asteroid impact. We could very easily be wiped out by an asteroid impact. But systems like Pan-STARRS and Atlas, try to make sure that there will be no deep impact in the future. But hopefully, in the process, while I'm saving the planet from destruction, right, I'm also hoping that I get to do a little bit of science. And so, thank you very much for listening to me. If you have questions, I don't know if you want to entertain them or come up and ask me if you're shy. Questions? Yes. In which? Sorry. Oh, asteroids. Which filter? Okay, so the question is in which wavelength do we try to find the asteroids? And we use basically visible light. Yeah, R band. Yeah, technically it's the R band, or even a wide band, but most people use an R band. Like, there's another question. Yeah.
Yes. You said that because of the daylight, we can find just 60% of the objects we have out there. Is possible to have in the future some, for example, space-based technology to confine to cover all the space we have out there?
Yeah. So the question was, the Atlas would only find 60% of the asteroids before they impact, and so is there some way maybe to have a space-based spacecraft that did not have the limitation of not being able to look at the sun? And the answer is yes, it's possible, and there are people who are working on this kind of technology now. There are people who have proposals to NASA to build these kind of spacecraft and launch them. The problem is money, is convincing people that we know how to do it, that the problem is there, and then convincing them to give us the money to do it. And what we really want to do is we would want to put a spacecraft in a Venus-like orbit, not in a spacecraft around Venus, because Venus is very bright and complicated, but we would like to have a spacecraft that is interior to the Earth, looking outwards. And that way we can see all the asteroids that can come close to us. And that turns out to be a very efficient way of doing it, but it's also a very expensive way. One spacecraft in a Venus-like orbit could solve the problem in about 10 years. In about 10 years we would know all the dangerous asteroids. Whereas from the Earth, using current technologies and even using the technologies that we were just planning, would still take 100 or 200 years to do that. All right, well, thank you very much.
What's about the small telescope? Is it possible to use for this kind of research? I mean, for instance, a reflector, 16-inch, maybe?
So the question is, what is the utility, the usefulness of using small telescopes for this kind of work? And I think that, like I said, right now, 95% or more of all the asteroid discoveries are done by just 3 telescopes in the world right now. One of them is Pan-STARRS 1, the one I'm on, and then there's other 2 by this Catalina Sky Survey. 95%. So the opportunity for a small telescope to discover these asteroids is limited, very small. I mean, people do it because they're interested. Doing it from the southern hemisphere is not a bad idea, because all the big telescope surveys are in the northern hemisphere. So in the southern hemisphere, especially if you target the area that is not visible from the northern hemisphere, you have a not bad chance of finding something. The rate you will find them at will be very small, but you will find bright ones that are important. In fact, I know a guy in Chile who's just starting with a 24-inch telescope to do this outside of San Pedro de Atacama. But the other good thing that smaller telescopes can do is that once the big telescopes find them, we do not often have the time to follow the objects. And just finding an object does not mean anything. You have to follow it over days, weeks, months, years in order to be able to predict its orbit very accurately. And so for the follow-up, after we discover the objects, we depend upon a lot of amateur astronomers to do this. But even those amateurs, the smallest telescope they would use might be a 16-inch telescope.
Yes, this means this is useful for a complementary work to follow the asteroids.
Yes, the smaller telescopes are great for the complementary work of follow-up.
Small question is related with the frequency of this kind of impacts on the low latitude, for instance, over the equatorial regions. How often is this taking place, this kind of impact?
Yeah. No, I have an image I can show you afterwards, but in fact there is almost no difference with latitude. So it's not like you might think Ecuador is either protected or unprotected because it's on the equator. There's almost no difference with latitude. Because remember, the Earth seems large to us. You know, it's 8,000, 10,000 kilometers in diameter, right? So it seems very large to us because it takes us a long time to go anywhere. But the Earth is still very small compared to the distribution of asteroids, right? So the distribution of, the Earth is this big, and then the asteroids fill up this volume. And so they can come down from the top as easily as they can come in from the side. The probability is the same with latitude. Yes.
Do you have another question?
Yes. Thanks. Right now, the only thing we can do is to evacuate. But in the future, is there a possibility we can somehow send an asteroid into another orbit?
Yes, so for the very biggest asteroids, the ones we know 90% of all the asteroids 1 kilometer in diameter or larger. And those ones we know, the big ones are sort of easy to find now. They used to be difficult to find, but they're easy to find. And for those objects, we can predict their orbits hundreds of years into the future. and we know where they are. And if we found now an object, a new 1 kilometer diameter object that was going to hit the Earth, in 200 years, we could probably deflect it if we wanted to. And in fact, it's actually an interesting question, because do you have the same superstition here with Friday, April the 13th?
Yes.
Okay. So on Friday, on geosynchronous satellites. Right? So the satellites that we use that provide your satellite TV, right? That you have a dish on your apartment or your house that points up to a satellite, right? Those satellites are about 40,000 kilometers high. And on Friday, April the 13th, 2029, a 400-meter diameter asteroid is going to go underneath them. It will be visible to the naked eye if you are in Europe that night. Okay, so if you want to see an asteroid with your naked eye going across the sky, arrange to be in Europe that night. The reason I bring it up is because we know that the asteroid is not going to hit the Earth in 2029. But there's a 1 in 10,000 chance that it will hit the Earth in 2036. Okay? And the thing that determines whether or not it hits the Earth in 2036 is exactly where that asteroid goes when it passes the Earth in 2029. If it passes the Earth, well, so imagine there's let's say that this whole area here is where the asteroid could go. And if the asteroid goes anywhere out here, it will not hit the Earth in 2036. But if the asteroid passes right through the dot on the eye, okay, then it will hit the Earth in 2036. Now, we don't know where it's going to hit, where it's going to go by the Earth. But we know that there's a 1 in 10,000 chance it will go through that dot in 2029. If it goes through that dot in 2029, then it will be on exactly the right course that it will hit in 2036. So there is the chance that we may have to find a way to deflect this asteroid. And to do that, there are ideas how to do it with a spacecraft. The most easiest thing to imagine is that you detonate a bomb. You blow up a bomb near it. You do not want to blow it up, because if you blow it up, rather than having one bullet hit the Earth, you have a whole bunch of material hit the Earth. So it's the same amount of material, just spread over a larger area. So what you want to do is you want to blow up a bomb near it and push it off its orbit and move it into a new orbit. There are other ideas as well, but that's the easiest to explain. Well, thank you for listening. Appreciate it.
Thank you.